In the last video, we did one-dimensional array, 1D, and did the bubble sort. Today, we are going to, in this video, we are going to learn about two-dimensional arrays. So in two-dimensional arrays, you have more than one column. In one-dimensional array, you saw that there is only one column and the different rows were called elements. Element 1, element 2, like that. But whereas in two-dimensional, that means more than one column. Not only two columns. When you say two-dimensional, more than one. Any number of columns you can have. But first, earlier, you used to say board and within square bracket, just one number, which was the element number. But now you can't do that because there are several columns like this, and then you don't know which one it is unless you give two coordinates. So first the row. These are the rows horizontally, and the columns have vertically. You have to give the row first, row number first, and then the column number, so that it will be like row, column, column. Row, comma, column. The lower and upper bounds for each dimension. In the one-dimensional, there was the lower bound, that is the first element, and then the upper bound of the last element. So here you have two sets. One for the rows. One is the first row, and generally it's one. And the upper bound of the rows, what is the maximum number of rows? Same way, column, lower bound and the upper bound. Game board of 6 rows and 7 columns. This is the way to declare. Declare board, and this is the column. The colon, to say that the type. Just show like column. Declare board. Board is the name, the identifier of the array. And this is a keyword array. The within square brackets, you have the rows, lower bound and upper bound, 1 to 6, and comma, right? Comma, not colon here. 1 to 6 is a colon. And the columns, 1 to 7. In between the column, to separate the rows and the columns, in between is a comma. I will highlight that also, then you see. The comma will separate the rows and the columns. And as usual, of integer, the type. What is the type of the array data? So while after doing that, board 3, 4 equals 0. That means it's the element in row 3 and column 4 to 0 will be row 3 is here, column 4 is this. So where the intersection is, where they meet, that's 0. That is how we assign 0 into this. When working with a 2D array, we need a loop to access each row. Within each row, we need to access each column. This means we use a loop within a loop. Remember, loop within a loop, a nested loop. That's called a nested loop. So when working with a 2D array, we need a loop to access each row. Within each row, we need to access each column. This means we use a loop within a loop, nested loops. In structured English, it will be like this. For each row, for each column, assign the initial value to the element at the current position. So let's have a look at the nodes. Yes. Now, this is a two-dimensional array with the names on the first column. You get the names. Second column, the marks, and the third column, grades. So rows 1, 2, 3, 4, 5 rows and 1, 2, 3 columns. So if say declare marks, if marks is the name of this array, colon array 1 to 5, that is always rows first, remember 1 to 5 rows and 1 to 3 columns. And then Tom marks within brackets 2, that is second row, and first column, that is this, is Tom. In marks 1, 2, that is first row, second column be 80. Marks 4, 3, that is the fourth row and column 3, C. Marks 4, 2, fourth row, second column, 65. That's the way it goes. Now let's see how we are going to, if you want to access, how do you access this? No? Or if you want to put all zeros here or something programmatically, right? How are we going to do that? So we learned that you need two loops, one loop within another loop, one for the rows and another one for the columns. So let's start with for row equals 1 to 6. It has to be outside because rows, when you start with the first row 1, column 2, first row, column 3, first row, column 4, likewise it goes. Then only you go to the next row. So the next row, that's the outer column. And this inner column, loop is the columns, for the columns. So for col equals 1 to 7, then both row, comma, column. So first time it will be row is 1 and column is 1. So that will be here. And if you input like row number and means this is the concatenation in pseudocode, ampersand. You can even have comma or you can have a plus sign. I'm using ampersand here because we are using a comma here as a string constant. Because I want the row number, comma, column number in this, right? So that will be this statement, the very first time when this is executed first time, it will be 1 and 1. That is row 1, that is this one. The row is 1 and the column is 1. Next time what happens? Row is 1. Still row is 1 because this outer loop will change only once it comes here for the second row. Still it's 1, row 1, but column has changed because this is next call. Next call will make this 2 now. That is why you get that. Then the next one is still first row, but third column. Then first row, fourth column. Row fifth, first row sixth, and first row seventh column. Then what happens? This loop is finished. This loop ends. Then it has to exit. When it exits, go to the next row. So next row becomes 2. Row 2 and column 1. Here, the row becomes 2 and the column is 1. The next one, row is 2 and column is 2. Row 2, column 3. Row 2, column 4. Row 2, column 5. Likewise, it goes. Then when it finishes, it comes to the third row. And so on, right? It goes on like that. Then what? Imagine that you have to, now this is not using an array, but just an exercise. If you want first, three asterisks here in the first row and $3 in the second row. How do we do that? So row 5, column 3 to be for the rows, number of rows may be 5, columns equals 3, right? 3 columns here, and the thing is asterisk. So for row equals 1 to 5. Row equals, this is something not in the pseudocode. This is something else, but just to show. So for row equals 1 to 5, that is for 5 rows here. Then if row equals 1, huh? If row equals 1, then the symbol equals asterisk. Else if row equals 2, then symbol equals dollar. Right? So end if, and then for column equals 1 to 3. For column equals 1 to 3, and then you go on doing this. So first time it will be the asterisk because its row is 1. 1 to 5 and it's go. This is just only a part of this, part of a pseudocode here, just to indicate without a 2D array, we are going to have these 3 here. Then the next time when it comes, when the column equals, row equals 2 in this loop, then it changes to $sign. So now the $signs are printed 3. It's not complete, these are just a part of it to show how you can do that. Then when you get back here, yeah, we did this up to this point, how you do. And then this is the one that I showed earlier in the notes, this one. Now there is a worked example, 13.04 from the textbook, working with 2-dimensional arrays and nested loops. Using pseudocode, the algorithm to set each element of array, this table, the array name is this table, to 0, right? For row equals 0 to max row index. For column equals 0 to max column index. This table, row column equals 0. So instead of, I did it in, earlier we did row and column both. But here we are assigning each element 0. For each element, the row and column, 0. We need the identifier shown like this. This table, that's an array, 3 columns and 5 rows. Table data structure, the 2D array, to store the values. Then we have the max row index. That is a maximum, the upper bound. Then the max column index, integer. That is the upper bound of the column index. The upper bound of row index first, and then the column index. Row and column. Counter for the row and counter for the column index. When we want to output the contents of a 2D array, we again need nested loops. Obviously, when we have to access the same way and then output. One is inputting, we are assigning values. Now we are outputting same way. We want to output all the values in one row of the array on the same line. At the end of the row, we want to output a new line. So first now for example, if you are doing these 3 asterisks, as I showed you in the notes, like this. How are you going to? Because every time you say output symbol, and the next one goes on to the next line. So we have to keep it on the same row also. We'll learn that also now. You may be already knowing. And then we have to go to the next line when the rows changes. Then for row equals 0 to max row index, then same way the 2 loops are going. This is the way when you first time you say this table row comma column, the asterisk or whatever the symbol or the number, whatever that will print. Instead of sending to the next line, we can say stay on same line. In programming, you have different ways. In Python, there is end equals blank, but in pseudocode, easy. Just put two slashes, that is for the comment. In pseudocode, this is the way to give comments, and then say stay on same line. Once that is finished, once the 3 columns are finished, then output new line means move to next line for next row. For the next row, start with a new line. So it's easy. Have a good look, then you will understand. Then declare a 2D array to store the board data for the game noughts and crosses. The empty squares of the board are to be represented by a space. Player A's counters are to be represented by O. Player B's counters are to be represented by X. Initialize the array to start with each square being empty. Initialize the array to start with each square being empty. So let's do that now. Yeah. Yes. So using those things, why is this 0 to 2, 0 to 2? Because, or you can even make it 1 to 3. Right? Sometimes 1 to 3 or 0 to 2. That's a board. For noughts and crosses, you know that tic-tac-toe, something like that. Only nine squares are there. 3 rows and 3 columns. So for row equals 0 to max row index is, we have to say 3, yeah? Because we have already, okay. And for column equals 0 to max column index, that's also 3 by 3. This table, row comma column equals blank. That's a blank. So we are initializing the board with all blanks and stay on the same line until you finish all the columns. When you finish the columns, that is 3 columns, output new line, which will move to the next row. Then the second row, again, 3 columns on the same line, blanks, then go to the next row and go to the next line and then output. That is the way it will be done. So, but here the first part is only initialize the array to start with each square being empty. So that we have done. Second one, write a statement to represent player A, placing their counter in the top left square. How do we do that? We'll have this side by side, then it's easy. Yeah, okay. So here you can say initialize the array to start. When write a statement to represent player A, placing their counter in the top left square. So A is, now we'll have to check. Player A's counters represented with O. Big O, right? B is X. So here it says, right, A, placing the counter in the top left square. So top left square is what? What is it? What do you call the for task 13.06, you have to declare a 2D array, right? So this is the way. For one, just declare board colon array 1 to 3, comma 1 to 3, 3 rows and 3 columns of char. Because just we are going to have either blank here or just the O and X, the symbols of each player. So just one character. So of char or character is okay, appropriate. Second one, initialize the array to start with each square being empty. So you can't be saying 1, 1 equals m blank, 1, 2 equals blank. You can't do that. So you will be doing something like this automatically to go to each cell or element and put a blank. So as usual, for row equals 1 to max index is 3. Then column, the second loop in a loop 1 to 3. Board, row, comma, column. That will be first one is 1 equals 1 equals blank. So this is for the later, right? For the next one. Yeah? In this case, blank. So here blank, then the second one blank, blank, blank. Go to the second row, blank, blank, blank. Third row, blank, blank, blank. That is how you initialize. Initialize the array to start with each square being empty. Then question 3. Write a statement to represent player A, placing their counter in the top left square. So that's here. No? O. Top left. Is this? So what is the location? The coordinates. Board is the name of the array, board. within square brackets 1 comma 1, no? First row, first column equals this O. And the second one, this one, write a statement to third one, so fourth one. Represent player A, player B, placing their counter in the middle square. So middle square is here, X in that. B is X, no? It says at the beginning here, represented by X. So that will be both second row, second column. Second row is this, second column is that. So the intersection is here, middle equals X. So that's done. Yeah, having done that, now we are coming to another word example, creating a program to play Connect 4. I hope you know this game, Connect 4. Then it's easy if you know it. Connect 4 is a game played by two players. In the commercial version shown in figure 13.06, one player uses red tokens and the other uses black. Each player has 21 tokens. The game board is a vertical grid of 6 rows and 7 columns. So 6 into 7 is 42. There are 42 slots. And each player has 21 tokens to fill up the board if you can't win before that, right? In case you don't know this game, you can go through the website, our course page, and have a look at a short video explaining the game. This is the website, and can go up to chapter 12, chapter 13. There you will find this video, Connect 4 game here. When you click this, you will get a video on how this game is played, the rules and everything. Like this. How to play Connect 4. But anyway,
Set up the board. Each player picks.
So anyway, you can do that video free, but I will just give a brief briefing on how to do it. What happens is one player would sit. Okay, here columns get filled with tokens from the bottom. So the first player will drop one here. It goes there. There's a groove here. There's a gap here. There are two surfaces here. So when you drop there, it will go down to the very bottom. And the next player drops. And the winner is something like this. So you have 4. That's why they say Connect 4. 4 either horizontally, vertically, or diagonally. But then we are not handling diagonally in this section. Just we are going to solve the problem of, we are going to have winners only of horizontal and vertical. So you have to, the game is like the other player has to prevent. Now supposing this 1, 2, 3, when the third one comes here, the black one somehow should put it here, his token here, so that he can't make a 4 in a row, 4 in line, Connect 4. You have to prevent the other player getting 4 in a row. So columns get filled with tokens from the bottom. The players take it in turn to choose a column that is not full. If it is full, you can't. In case this is another 2 tokens being put here, it's full, then you can't put. So you'll have to select a column that is not full. The winner is the player who is the first to connect 4 of their own tokens in a horizontal, vertical, or diagonal line. If all tokens have been used and neither player has connected 4 tokens, the game ends in a draw. So the board is full, but nobody could find 4 in a row. If we want to write a program to play this game on a computer, we need to work out the steps required to solve the problem. That means to let players take their turn in placing tokens and checking for a winner. We will designate our players and their tokens by O and X. So it's easy now. We are familiar with O and X there, like the earlier one. The game board will be represented by a 2D array. To simplify the problem, the winner is the player who is the first to connect 4 of their tokens horizontally or vertically, leaving out the diagonal one because it's difficult. Our first attempt in structured English. Initialize board. Yes, first we have to set up the board. Then set up game. Set up the game. Display board. While game not finished. So you go on doing these things. This is the main program. While the game is not finished, player makes a move. Then every time the player makes a move, you have to display the board, the updated board. Check if game is finished, and you have to check whether that last move finished the game. If game not finished, swap player. And the last one to be done here is swap the player. So if it was O first, now it's X. That is the next time when the loop the iterates, the second iteration, if the first one was O, now it's X. Likewise, it alternatively, each player gets his or her turn. So the top level pseudocode version using modules is, and using modules, now you know about modules, the subroutines, procedures and functions. So the way to execute or include a function or a procedure in pseudocode is call. The keyword is call. Call initialize board. So we have a set of instructions for this somewhere else defined, and we call it by that name. So call initialize board. Call set afterwards. It will, when this happens, after the first execution of this first line, it will not go to second. It will go looking for initialize board somewhere else, right? Somewhere else we'll have all these things, this setup board and see initialize board. Somewhere else it is defined. So it will go there and do that. Once you finish that, it will come back and do the second line. Here again, you get something else, setup game. So you go to setup game here. And then it will do the setup game. Once it is finished here, you go back here to the next one. Call output board to display the board on the screen. So again, it will be there, not in the main program. Now we are from the main program, we are coming here. Procedure output board, do these things, finish, and after the end procedure, it will not go there to the next one here. It will go back. That's how the execution takes place. The control comes here back. Then you start the loop in the main program. While game finish equals false, do call player makes move, call. So all these are there, right? We'll find call output board, call check game finish. If game finished equals false, then call swap this player, right? And while. So this loop will go on until the game is finished. Note that steps 3 and 6 are the same. 3 is call output board and 6 call output board. See, there are 2. This means that we can save ourselves some effort. We only need to define this module once, but can call it from more than one place. This is one of the advantages of using modules. So modular programming, modules. So here, instead of writing, now if we didn't do this, say output board is here. 1, 2, 3, 4, 5, 6. 6 lines. If we didn't do the according to modules or modular programming, then we'll have to have these 6 lines here. 6 lines there. Then again here also another 6 lines. Whereas we have only 2 here. So 6 and 6, 12. Out of 12 lines, we are having only 2 here. We have saved 10. So that's an advantage, definite advantage of using modules. All right, now we'll look at the identifier table. The identifier table is very important. Board, 6 rows and 7 columns. Initialize board, that's a procedure. Set up game procedure. Game finished. Boolean, that's if it is false, that means game is not finished. And if it true, the board is full or a player has won. In either case, right? Either the board is full or board is full and no winner, or board is not full but a winner is there. Player has won. Otherwise, if it is false, that means game is not finished. We have to go on. In this player, the current player, so it's char or character. Once it is O, then X. The next one is X, O, X. Alternative, taking turns, the 2 players. The output board is a procedure. Player makes move procedure. Check game finish procedure. Swap this player procedure. So we start with like this. Procedure, initialize board. Go through individual procedures now. For row equals 1 to 6, for column equals 1 to 7. This is easy. You have already done this kind of thing. Board, row, column, row, comma, column equals blank. Use a suitable value for the blank. So here we can use this blank. Space, blank space. And the next column. So this is about the 3rd time we are doing something like this. So it's easy. That is, when you finish that, you come back to that place, right? Yeah. Here. Then call setup. Setup game. Where is setup game? Here, setup game. What happens in setup game? This player equals O. So the starting player is O. Player O always starts. Then game finished. So if this is a program, then since we have given when the setup game, when setting up the game, we are setting that O has to start. So every time it will be O until we change the program. Then also another thing we are initializing, game finished equals false, a Boolean identifier or variable. Game finished is false. So it is beginning, end procedure and go back. Then it will say while output board, all output board. Here it is. So as usual, the 2 loops are there. Then in a loop, output board, row, comma, column, they won't move to next line. So whatever that is there in the board, whether it's blank, whether it's X or O, the players, that should come out onto the screen to show the position of the current board. Then, of course, when again, I'm telling you the columns finished, go to the next row, new line. Then come back here, after outputting the board. Then you do this. While game finished is false. So while game is not finished, call play makes move. Player makes move. What is that? Player makes move. That is the next procedure. Valid column equals player chooses column. So there's a module returns column number. The valid column equals, this is another procedure. So then you'll have to look for that. Player chooses column. A little bit difficult here. Player chooses. Here it is. Right. Function. And it's a function. Player chooses column and function, as you know, returns value. No? There's a return value. So you have to say returns integer. The type also you have to tell. Returns a valid column number. Output player, this player's turn. Output player O's turn or player X's turn. Right? And then repeat output, enter a valid column. Enter a valid column and then input column number. So the player will give a row, enter a column number until column number valid equals true. So here's another one. Check whether the column number is valid. So we have to go looking for column number valid. That is also will be there. Here, column number valid. So there you will check. I'm not going into details now, but you have to do it. You have to do this and try to understand, because otherwise it will take a very long time to finish this. But in your free time, you can do this. So I'm telling you only the important ones. Now, once you find the valid, it will tell whether it's valid or not. So when it becomes true, then return column number. Return column number, you have already done these kind of things. Return column number will give the value to this. Player chooses. We came to player chooses column number. And then we came to column number valid. Yeah. So then it will tell whether it's valid or not. Valid or not. So column number valid, then this will finish. This will exit. And then go back to player chooses, where the player chooses column that thing was there here. Yeah, player may export there. Then again, so if the player has chosen a valid column, until we saw that until the column valid equals true, you go on in a loop. The player has to input the column number. Once it is finished, then you come back. That move is done. Then check out call output board. So we already saw how the output board was done. And then check game finished. If game finished equals false, then swap this player and end while. So all these things we have to go through one by one and see what happens. We'll just go through in sequence, not in the program order, but this is designed, I think, in program order. So setup game we did, output board we did, procedure player makes move. See? Valid column equals player chooses column. So returns a column number means like function. So this is a function. Player chooses column. You saw it as a function, no? Here, player chooses column. It's a function and returns a valid column number. So here the valid column equals player chooses number. This will return column number into this. That is how valid column will be assigned. The column number will be assigned to valid column. Same way, valid row, find free row. So that's another function. Go back. Then board, valid row, valid column equals this player. Row is valid, column is valid, then X or O, the player's token, will be placed in this at that point. Then you find this column and the row. Then yeah, this one is column number valid. That how do you check whether the column number is valid? This we did. The column number is valid. Returns whether or not the column number is valid. So starting with valid equals false. If column number is greater or equal to 1 and column number less or equal to 7. So that means, okay, no? 1 to 7 column number is valid. No? If not, don't do any of these things. If it is either 0 or -1, or from this side, if it is 8, 9, 10, none of these will happen. But if it is valid column number, then if board 6 column number, why is that 6? You notice that this starts from the bottom. When you drop a token, it will go down. So down means now if this is the array, which row? 1, 2, 3, 4, 5, 6. Row 6. Unlike the normal array starts from here. But these tokens cannot be suspended here in there. It will drop down, go to the last. So starting from the last, coming down. So that is why it is yeah. So setup game also, this output board, did you notice that? For row equals 6 down to 1, not 1 to 6. Down to, you must be knowing by now, for next, generally 1 to 6 and step 1. Generally, the step 1, we don't put step 1 because it's the default. Unless we want a different step, we don't put. If you want a different step, for example, 2, then you have to say step 2. This is just revision. You all know about this. Then columns, of course, left to right. So there is no problem. You don't have to start from the last one to the first. There is no case like that. Just check 1 to 7. Then output board, comma, row, comma, column. Don't move to next line. This is the output board. Remember, output board. So next column. Output new line. So that goes to the next one. Likewise, the whole board will be on the screen then. Then the player makes move. Valid column, we saw that. Valid column equals player chooses column. That's a function that will return the column when he input the correct one. Then valid row equals find free row. That's another function which will give whether the row is free at that time. If both are okay, then this player will be assigned either X or O. Then we have some more. Valid column, it's an integer. The column number the player has chosen. Player chooses column integer, a function to get the current player's valid choice of column. This is the returning integer, right? Player chooses column. That's a function. Then valid row, also a function that will return the row number. The row number that represents the first free location in the chosen column. Find free row, function to find the next free location in the chosen column. Function player chooses column returns integer. So output player, if it is X, X's return. Then repeat, output enter a valid column number and input column number until column number valid equals true. So until this procedure, when we go to that procedure, we'll see how it is done. And when that happens, it will return the valid column number. Note that we need to define the function column number valid. A column is valid if it is within the range 1 to 7 inclusive, and there is still at least one empty location in that column. At least one. Function column number valid returns Boolean. So here the valid equals false, we start with that. Then if column number greater or equal to 7, we saw this earlier. Then if it is 1 to 7, then if board 6, comma, column number, the lowest one, equals blank, that means at least one empty space in column, because we don't know the row 6 means the last row. If it is blank, then at least there is one, because we don't know the column number. Whatever the column number that is coming. Then valid equals true. If this is not blank, then valid will be false, because we start with valid equals false. So if 6, that means the lowest one. And if it is there, then that means there is a end if and return valid. return valid. So that is valid column number here, return column number, right? So find free row, this row equals 1. While board, this row, comma, valid column not equal to blank 2. So if it's not equal, go on. This row equals this row plus 1. So the row number, this row number increases, and then when you repeat, it will go to the other row. Second row, third row, like that it goes on. Then finally, return this row. So if this row, what is the row number? Because this is increasing, it will it will return the blank, the next empty slot. Then procedure, check, game finished. Winner found equals false, starting with that. Call, check if player has won. So that's another function, right? We'll leave it there, and then otherwise it will confuse if I go there and then come back here. We finish this, then go back, go later. If winner found equals true, imagine that this function somehow returns. If it is true, then game finished is true. Output, this player is the winner, because this player is either X or O at that point. The current player is the winner. Else, call, check for full board. Then there's another one. Note that the check game finish procedure uses 2 further procedures that we need to define. Okay, 2 more procedures. These 2, we have to define them. Yeah. So here are the additional identifiers. Winner found Boolean, false if no winner, and true if a winning line is found. Check if player has won, that's another procedure. Check vertical line in valid column. Procedure to check if there is a winning vertical line in the column the last token was placed in. Check for full board. Procedure to check whether the board is full. So this is quite a long program. It's worthwhile if you can master this. Even if you can do it in Python even, that's fine. So then the procedure, check if player has won. Winner found equals false, then call, check horizontal line. So they will come later here. And if winner found equals false, then call, check vertical line. That is, if there is no horizontal line winner, then check the vertical line. So vertical line will come later. Check horizontal line. This is the way for I equals 1 to 4. For I equals 1 to 4, if board valid row, so we now have the valid rows already. This is a variable, comma I will be 1 here. This player and, so this player is either X or O. Let's imagine that is O. So if this element, this slot is O, and then this also, what is that? I plus 1. Same row, valid row, the same row number is there on the same row, because we are checking horizontal, so we have to go the next column, I plus 1. If it is O and like that, all 4. If it is O, then the winner is found. Okay, winner found equals true. End if, and then next type, that means you go on. Right? And procedure, the check vertical line. Similarly, you do 5. If valid 4, valid row equals 4, or valid row equals 5, or valid row equals 6, then if board valid row column, column equals this player. So if it is O, this is O, this is O, this is O, this is O, then again winner is found. So winner found equals true. Then what? Check for full board. So if these two are not still false, winner found is false here and winner found is false there also, that means winner is not found, no one and won. But every time we'll have to check whether the board has become full, then we'll have to stop. Because you can't, the other player can't play. No one can play then. So procedure check for full board. Blank found equals false. This row equals 0. Repeat. This column equals 0. This row equals this row plus 1. And repeat. This column equals this column plus 1. If board, this row, this column equals blank. So you check whether there is any blank. Blank found equals true. In fact, this you're going through the whole thing. And because there are two loops, can you see? Repeat until this row equals 6 or blank found equals true. Inner loop, repeat until this column equals 7 or blank found equals true. So what you do is you check each element if there is a blank. If found, then blank found equals true. And if blank found equals false, then output false means that it's full, no? Not a single empty slot in the board. Then in that case, output, it is a draw. It is a draw. So no one has won. And also game finish equals true. Game finish equals true. Why is that? Because here in the main program, it says until while game finish equals false. Go on playing the game until game finish equals false. But now we are finding game finish true because the board is full or winner found or whatever it is. Yeah, game finish equals true, then the game will finish. So we have some more, like how do you swap this player? Because swap player came somewhere there. So if this player equals O, then this player becomes X. Otherwise, this becomes O. So it's a very easy thing. We can also use arrays of records. So this is different. Huh? Now that is finished. Now this is another one. We can also use arrays of records. Using the person record type from section 13.02, we can declare an array of that type for 100 person records. How? Now you'll have to refresh your memory, because when you say what is this person type, if it is person type, you remember there is a book type. If it is book type, let's say imagine you can have book.title equals computer science, book.year equals this, book.price equals that, and the book ISBN is this. The 4 fields of this book type record. But if you want to enter another book, this will be erased. Computer science will be erased and the new title will come, and the second year of publication will come. Likewise, there's like A equals 10. And if you want to put another value, A equals 20, that A will be erased. 10 will be erased. So what do? We have to declare an array. When we want to say 5 numbers instead of N1, N2, N3, N4, and 5, what we do is array name, and then within brackets, you use the element numbers 1 to 5. Similarly, if you want more books to be stored or more persons to be stored in that, then we have to have an array. So my book, in this case, it's my book, array 1 to 100 of book type. So this every element will be like this. Like the title, year of publication, price, ISBN to be a record like that. Okay. Want another table, then the second row, third row, likewise, there are 100 columns. Actually, this is one record. We want 100 rows like that. Okay. Yeah. So first person's name in the array. So if you declare person array 1 to 100 of person type, that means this is the 1D array. 1D array, no? So 100 elements. But imagine you have to picture like this. 100 elements. This is one element. Don't think of this as a 2D array because we are giving only one lower bound and upper bound. There's only one dimension. Only one dimension. But in that first element is like a record like this. Second element also becomes a array. So this 100, the upper bound 100 means that there are 100. If you like, you can think of rows or records. Say records, 100 records. So the very first one will be after declaring this 100 of person type. So person type is what we have defined here. Now here it's book type. We remember the person type, the name and all that were there. So first person's name in the array is set as follows. Person, element 1. Person, square brackets, element 1. And then the dot notation. Remember dot notation. Dot name is Fred. And the output, if you want to output, person 1 dot name. And the name Fred will be output. So if you want to have person 2, then person is brackets 2 and the name, second person's name. So here's a task, 13.07, declare an array of book type. Okay. Or for 200 books, array of book type. See, not the one that we did earlier, like something like this. Declare person, we have to declare book, an array of book type. Of book type. Right? Set the first book's details to the values given in task 13.02. So that's the last one. So this should be easy for you. How you do that is person the first one. This is the first book only you have to do. So you don't have need any loops or anything. Just person, book like this. Book number and book 1 price like this. Book visit square brackets 1 dot title, right, equals, and then whatever the details given in 13.02, remember that all those details to be given. All right, so then we come to a different section, new section, text files. What are we doing? Data structures. So in the text file also you can save data. Arrays are only in main memory and are temporary. Okay, that we learned earlier. Let's see whether it is there in this also. Here. Array in RAM, file on hard disk. So if you use arrays, every time you run the program, you have to enter data. You can't save anything. If you want the previous game's details, then what you have to do, you have a file on the hard disk. Then only you can recall that data and then have it this time. So now we are coming to, now we just finished this one. Text files. How are we going to handle text files? They have to be saved, right? The arrays are only in main memory and are temporary. If you want, then they have to be saved in files on hard disk for future use. A text file consists of a sequence of characters formatted into lines. Each line is terminated by an end of line marker. The text file is terminated by an end of file marker. So the line, end of line, and the full thing. Okay? End of line, each line is terminated by an end of line marker. The text file is terminated by an end of file marker. So EOF, it's called EOF. The line has an end of line, EOL, and then EOF for the file, whole file. Otherwise, the program doesn't know if your program is using that file. If we just open up a notepad and then that's a different matter. Notepad is the thing that we can save text. Writing to a text file. Writing to a text file, we are going to handle reading from a text file, appending to a text file, and these three. Write, read, and append. Those are the three. It's very easy to remember. Open file is the first thing here. In all three, see, whether you want to write, read, and append. You will see the difference between write and append later. Both are writing on the text or on the file. Reading is reading from the file. So is open file, it's easy. All three in common. Then the file name, same. It's also same. File name you have to give. For write, this is the only difference. For is there, for, and this is write, this is read, if you want to read, and this is append, if you want to append. Okay. Then write file, that's a command. Write on the hard disk, the file. Write file, and the file name is there. And the comma is a comma and text string. Text string will have some data. Write a line of text to the file. This text string will be written to the file. Then finally, close file, file name. You have to close file and you have to give the file name. Remember, just close file won't do because there may be other files open at that time. So which one you have to tell. So then reading, what happens? Open file, file name, for read, then file name, comma, text string is the same. So it will read from the file one line and put it into the text string. Read a line of text from the file and then close file. Appending. For append, same file name, text string, write file. Here, of course, read file. The difference is that is read file and this and that, both it's write file. But here it's different. This is for append and this is for write. So syntax here is the same. Write a line of text to the file, close file. The difference here is when you write to a text file, every time you run the program, this file name will be accessed and erased, the earlier data. When you write, it will be always new. Erase the old contents and do it like a replacement. But here, the append, in the append mode, it will not erase. It will be there and append. As the word says append, you add at the end. So it goes on, and that's the way. And the end of file marker. End of file marker, EOF. Testing for this special end of file marker is a standard function in many programming languages. The function will return false if the end of the file is not yet reached and will return true if the end of file marker has been reached. So true or false. Is the end of file, is it true or false? Then only the program will proceed beyond that. In pseudocode, we call this function EOF function. EOF and the two brackets. All the functions should be having these two brackets. To read the text file and output its contents. How? Read the file and then output its content. Open file, this is the name of the file, test.txt. For read, while not end of file. So this is the way you have the loop. The condition is while it's not end of file, do this. End of file, which file? This one. End of test.txt. Do read file test string, the file name test.txt and the comma and the text string. So it will be read to this one. And output text string. It will output this, whatever the line that was read. End while. Then close file text. Okay. Even though these three are together, they need not be together everywhere because there may be, if open file comes here, then it will be opening, and close file comes here, closing with every iteration, but it's not necessary. Just open once and then do whatever the processing you want, then finish and close. Then the task 13.08 is write pseudocode to save the array data from task 13.06 to a text file. Write pseudocode to read the values stored in the text file back into the board array. So this is something that you must do on your own. It's easy if you follow. And also, you're supposed to read these, follow it, and then do this. That's also part of the training given here. So now we are going into a new type called abstract data types. Remember, this is the data representation we are doing, data structures and all that. Structures. So this is another type of structure. It's called abstract data types, ADTs. An abstract data type is a collection of data and a set of associated operations. So imagine now in a programming language, if you declare a variable as integer, you can't enter characters or strings into it. So that's a function of it, a quality or feature of that type. Same way here, an abstract data type is a collection of data and a set of associated operations. They also have set of associated operations. But this is not user-defined, right? Don't confuse with the user-defined data type. We learned about user-defined data types earlier, where we can define. So under this, under ADTs, so the three structures will be dealing under ADTs will be stack, queue, and linked list. Stack, queue, and linked list. They can be implemented from arrays. Create a new instance of the data structure. Create a new instance of the data structure. Find an element in the data structure. Insert a new element into the data structure. Delete an element from the data structure. So all these we can do. Access all elements stored in the data structure in a systematic manner, in order. Otherwise, we can create a new instance, then also find an element which is already there, then insert a new element, or delete what is not necessary. So abstract data type is a collection of data with associated operations. That's a summary of the definition there. Then stack. First of all, we'll take stacks, and you will know, you would have seen this at hotels and all that, when there is a buffet meal, the hotel, the waiters will come and put the plates like this into a hole here. And the first plate has gone down, right down somewhere here. It will be there under the table here. Second afterwards, third afterwards, and this is the last. So when you take a plate, you take the last or the first. You can't take the first because it's right underneath. You have to take the last. So it's like last in, first out. That's the basis on how the stacks work. So here's an empty stack. Left is an empty stack, and a stack with 4 items pushed. Right side. The pushed is the term to say push, insert, and pop. Later we'll know. Pop is the one that if you want to delete one, the top one, only the top one you can do. That's called a pop. So pop and push, right? Pop and push are the 2 terms used. Now look at this empty stack. There are 2 pointers in stacks: base of stack pointer and top of stack pointer. When an empty stack, the base of stack pointer is 0, and the top of stack pointer is -1, even below 0. Top of stack pointer is -1. When A is inserted here, that is only, there is only one. Imagine B, C, D not there yet. A, the only one element is there. Then what happens? the base of stack pointer is still 0. Base of stack pointer is still 0, but the top of stack pointer will move up 1. So that also will be 0, no? Because this is minus 1. And if you add 1 to it, it becomes 0. So where there is only one node or element, there is both top of stack pointer and base of stack pointer will be 0. When B is pushed into it, B is pushed or inserted, base of stack pointer is still there, but the top of stack pointer will move to 1 here, starting from 0 going up to 7. Likewise, when D comes, the top of stack pointer is there, 3. Base of stack pointer won't move. Base is base, that's all. It doesn't change. When the stack is empty, top of stack pointer will have the value minus 1. It's here, minus 1. So how do we declare an array of this to simulate a stack? Declare stack, we have given the name stack. Array is a type, and element 0 to 7. 0 to 7, 0 to 7 here of type char or character. Because we are going to have just one character there. Otherwise, if there are names, you can have of string. If you are having numbers, ages or something, then of integer, whatever. 13.09 task. Draw a diagram to show the contents of the stack shown in figure 30.07, that is this one, after E has been pushed onto the stack. So what happens? To draw, you'll have to draw this plus E here. And without the top of stack pointer here, you have to draw it there, right? Type of top of stack pointer will be here, pointing at E or element 4. Then draw a diagram to show the contents of the stack shown in figure 30.07 after one item has been popped off the stack. So E didn't come yet, right? Imagine, because figure, the stack shown in figure 30.07. So E is not shown here, no? That is our drawing. So here what happens, when you pop, after one item has been popped off the stack. So when you say pop, this D will go off and the top of stack pointer will be reduced to this 2. It will come down to 2. That is your answer. Then there is another structure called queues. How do queues work? Front of queue pointer here. Now see, the stack, we had the 0 down. Because starting, the first plate will be dropped here down. This is 0 down to 7. And the front of queue is at 0. End of queue pointer, as usual, minus 1. So when people join or items join, items are added. Say A is added. First of all, both will be 0 then. Front of queue pointer is 0, end of queue pointer is 0. Similarly, it will be done. You know already what happened in the stack. When B comes, still the front of queue is there. End of queue only will move. There is one difference. Right? One difference in this when you consider the stacks, when you compare with stacks. Here A will move out. First in, first out. First one to come here is the A, and A will move out. Then B will come up to the first place. Likewise, they join at the end and move from the front. Whereas in the stack, it was last in, first out, no, LIFO. This is FIFO, first in, first out. And, yeah, an empty queue left and a queue after 5 items have joined, right? When the queue is empty, the end of queue pointer will have the value minus 1. When the item at the front of the queue leaves, we need to move all the other items one slot forward and adjust end of queue pointer. So it's not a very efficient way. Though in real life it happens when the first one in the queue moves, all the others move up and take the B will take the first position, front of queue. We will see how you overcome that? How you make it more productive or efficient? By having a thing called circular queue. But before that, there is a task. Draw a diagram to show the contents of the queue after F has joined the non-empty queue from figure 30.08. So it's easy. You put F here and then move the end of queue pointer there. Draw a diagram to show the contents of the queue after one item has left the non-empty queue shown in here. So that means who is leaving? A or B? Only A. A can leave because he is at the front of the queue. So your diagram will have B here. B has moved there, C there, D, E. It will be A, B, C, D, E. And the end of queue pointer here, pointing at 3 or D. Easy. Then instead of moving items, because otherwise we have to move, no? One goes, all items have to be moved. That's not a very efficient thing. Instead of moving items, a circular queue. We call it a circular queue. Circular queue after 11. After 11 items have joined and 5 items have left the queue. Let's see what happens. Imagine the very first one, A, B, the position at the beginning, A, B, C, D, E, F, G, H. 7 have joined. Now I, there is no place here to join, for I to join. But when A moves, I will join there. So it's like a circular. The end will be connected to the beginning. Then B leaves and J joins here. C leaves, K joins here. L will be here. M will be here, right? Then they have left. M and O. Likewise, it will go on. So what will move? Both will move here. In the other two cases, only one was moving. But here, in this circular queue, both will move. Why? Because the front of queue, which was there at first, now it has come here. These are not moving. F did move up, right? F did move up to that place, but the pointer was directed to this. And similarly, end of queue will move. So when L comes here, this will come there. When F goes, front of queue will come to G. Not difficult. Now this is what we are going to do in detail. Linked lists. Instead of a linear list, another method is to store an individual list item in whatever location is available and link the individual item into an ordered sequence using pointers. So linear list is just, without any order, just having items. And then what happens? You'll have to move items. If one new item comes in, then you have to move all the others and insert it there like that. So that's also not a very efficient thing. A node can consist of several data items and a pointer. So this is a node. This is a conceptual diagram of a linked list. The node will have data as well as a pointer. A node can consist of several data items and a pointer. So remember those two, which is a variable that stores the address of the node it points to. So this is data and this is the pointer pointing at the next one in the list. And so that means this will be linked to this. And this will have the link to the next one. This will not have anything. It's called the null pointer. So these are pointers, this small square. This is a pointer without data. So start pointer is just a pointer, no data. The last one, data, they are, but no pointer. I mean, it's a null pointer. It's not pointing at anything. A pointer that does not point at anything is called a null pointer, or this is the symbol used. So let's have a look at illustration. It will be easy to Understand? Stack. You can go through this, but yeah, no need. It's all explained. We did this. Queue also here, like that. Then the linked list. You need some explanation there. This is where you don't have the order. There is no order, physical order as such. Only a logical order. How does it happen? Imagine that this is a garden party, and garden parties you don't sit. No. If you keep a row of chairs, each one, the one who comes first will sit on the first row, then the next one, second chair, third, like that. No, they will like to sit wherever they like and where they are friends or under a light, under a tree, the shade or various things can. But supposing, imagine this situation where a welcome drink or a number for a raffle draw or something like that. Just something is given, it has to be given in order. The first to come should get the first one, second to come should get second one. So how do we identify? If they go and sit everywhere, how do we identify how to give? If you send a waiter, who came first? You don't know. So for that, there is a pointer. The very first one sits here, say near a tree. Right? And then there is somebody pointing with an arrow or put an arrow and point at him. That's a start, the first one to come. Then the next one comes and goes a little away and sits near a pillar or something, right? Another table or something. That case, now this one, now the one who comes last won't know who came first, but the one who came first will know who came second. So this one will have a pointer at him. The second one. The second one will note the third one, who is the third one. Either red shirt or something like that, or some number, some kind of where he sits, he will make a note of it. So likewise, you will have, and the last one can't point at anyone until the next one comes. So this is like the null pointer. So there is no data here, no person here, but then arrow here pointing at the one. But here the person is there and the pointer is there. So like data and the pointer. Similarly, this also has the data and the pointer. This one has the data, but not pointing at anyone. That's the last node. So take an example like this. We have the letters L, B, T, C, M, A, and T. In case you want to have this in order, alphabetical order, what do? This is the start. There is no data here. There is no data. Starting, we are saying 5. Go to 5. So it will point at this 5. And that has A, the beginning, alphabetical order, the first one. This one, the node has the data A and the pointer is 1. So where is 1? It will be linked to this. This is why it's called linked list. There's a list is there and the links are there. So B is the second one. B will have 3 as the next next point. So where is the next point? 3. It's here. It will point to 3, which is C. And C will have 2. 2 is here D. D will have 0. 0 is here L. And then L will have 4. 4 is M. M will have 6. 6 is T. And that's the last one. So T doesn't have, it is not pointing at anything. It's the last one. So that's a -1. -1 is generally used for the null pointer. And there is a thing called free list. We'll learn later. Why? Because if you want to add a list, add a node to it, from where? Which one? You must have the address, no? You must have the address of the next node in order to link. Say here, this free list has 7, 8, 9, 10 nodes. You don't move this. If you want to add one to this one, you don't move this there. You just leave it there, but change this only. What do? Delete this and make it 7. So physically, you are not doing anything to this, just changing the 7 so that this will be linked. And if this has the node, the next node will be this. This will become the next node. Likewise, it goes on. So this is called the free list. It's very interesting. These are the operations that we'll be doing. It's described here. So this is a conceptual diagram of a linked list, the normal one. This figure shows how a new node A is inserted at the beginning of the list. A, maybe from the free list, this is the free list. A has to be inserted before B. This is B, D, L, right? B, D, L. So you have to have that, from the free list, you are going to link it. So if A is inserted at the beginning of the list, that means like before B, the content of start pointer is the pointer that is pointing at B, is copied into the new node's pointer field. New node is A here. From the free list, we have taken A. And start pointer is set to point to the new node A. So it's like breaking this link, this pointer, and then putting it into this point at A, right? And then A will have this address, what was there earlier, that address will be there, the B's location. So it will be like this. Going into A, start point will point at A will point at B, and the usual is still there. We have not moved anything. We have not moved them there and made a room here. No physical movement. So that's why it's efficient. Just changing the links, pointers. In figure 30.12, that's the next one. A new node P is inserted at the end of the list. The pointer field of node L points to the new node P. The pointer field of the new node P contains the null pointer. So if you want to insert P there at the end, all what we have to do is turn this is null pointer, point at this P, and then make the pointer here as null pointer. So that this becomes the last one. Similarly, what happens here? Delete the first node in the linked list. That means B. If you want to delete B, just break this off and connect this to this. Very simple. No removing, erasing, deleting, nothing there. Just break it and put it here. So that this is there. But the processor doesn't know. The program doesn't know that this is there because we are bypassing this. In other words, we are bypassing this and going there. So physically, nothing happens here, only the start pointer will change it, the way it is accessed. Next one, conceptual diagram of deleting the last node of a linked list. How do you delete the last node? This is the last node, which had the null pointer. You make this the null pointer. Now earlier D had something pointing at L. Now we make this the null pointer so that it will not point at anything. So this is ignored, simply ignored, deleted. Conceptual diagram of adding a new node into a linked list. Same thing. Like earlier we inserted here, and now we are inserting this here. Whatever it is, what to do is take that link and put it here and connect this to this. Point at the next one. So in between B and D, C will be inserted. Not inserted physically. In the list, the order will be that. When you process it, after B, the next node will be C. Conceptual diagram of deleting a node within a linked list. So similarly, earlier also we saw that. Just break this off and then bypass this. From B, you point at L. So D is ignored. Linked lists are preferable to linear lists. When list elements need reordering, only pointers need changing in a linked list. In a linear list, all data items would need to be moved. Correct? No? So because if you have to, if this was a linear list, sorry, If this was a linear list and you wanted to change it in, now it's at the moment it's in ascending order. If you want to make it in descending order, then all will have to move. T must come first and, But in a linked list, nothing moves, only the pointers will move. Instead of start pointer pointing at A, in the descending order, the first one will be T, So instead of 5, it will be 6. And after T, it will be M. So instead of this one having 7, this one, yeah, this earlier I made this change, so I change it back, right? Instead of having -1, it will point at 4. And M will point at L, that is 0. And where will the null pointer be? A. In a descending order, A is the last item. So instead of 1, A will have -1. See how easy it is. Instead of moving means it's a big job. Yeah. In a linear list, all data items would need to be moved. But in a linked list, no need. Using linked list saves time. However, we need more storage space for the pointer fields. So pointer fields, we need more storage space. That is on the other side. There is no perfect solution to anything. So advantages and disadvantages. To implement a linked list using arrays, we can use a 1D array to store the data and another 1D array to store the pointer. Like this, data in one array and pointer in another. A value is added to the next free element of the data array and pointers are adjusted to incorporate the node in the correct position within the linked list. So 13.7 figure, this one shows how two arrays can be used to implement the linked list from figure 13.10, the original one there, L, D, L, B, and D. What has happened here? Start pointer is 1, which means now the index is here 0, 1, 2, 3, like that. And 1 means B. B was the first, if you can remember. Here, I have copied it here, conceptual diagram. B is the first one, so pointing at 1. Then B points at this 2, which means D here. This is the index. This number is the index number, D. And then D points at 0. 0 is here L, and 0 points at nothing, -1, the null pointer. Have a good look again. You can watch the video again and again and see. It's easy. Then this one, adding a new node to the beginning of a linked list. What do you do? Earlier it was 1, which was B. But adding a new node to the beginning means before B, Before B, the A must come if we are adding A. But physically, we are just putting the next available. This is a free, the next available slot is 3 here. But if you want to make it first, then we have to change this start pointer to 3 so that it will point at A first. A will point at 1, which is B. B will point at 2, which is D, and D will point at 0, which is L, and L has a null pointer. Very easy. Very easy. But you have to do this on your own. And then only you will know whether you really understood or not. So what is this? Adding a new node to the end of a linked list implemented using arrays. So what do? You don't change the start pointer because starting is no change. Only you have to change the last one. You're adding P to make P has the null pointer and change the L's null pointer to 3, which is P. L will point at 3. The new value is 3 here. And P will have the null pointer. Deleting the first node in a linked list implemented using arrays. So as usual, the data is here pointed there. The start pointer is 1, but we want to delete that one. This is the original one. We want to delete B. What do? We don't erase or anything, just change this to 2 so that we bypass B and go to 2. You don't go to this one. go to 2. Start with 2 and then 2 will point at 0, which is L. That's all. L will not point at anything. So B is ignored. That is how you delete. Deleting the last node of a linked list implemented using arrays. Same. No change in the start, but the last one, early it was L was the last one. But now coming to B, going to D, and if D has null pointer, it will not point at L. L will be ignored. So here L is deleted. The last node is deleted. Adding a new node into a linked list implemented using arrays. Right? Same thing. Adding a new node into arrays like here what I have done? C. We have added C, and what is the change? Going to 1. B. B has, that means if you want to put in order, like, no? If you want to insert in the correct order, after B, C should come. So, instead of going to D, you make it 3, which will be C. So, B will point at 3 and C will point at 2, which is D. And D will point at 0, which is L. So, that's in alphabetical order. What is this? Deleting a node within a linked list implemented using arrays. So, what is the one that is deleted now here? Just see whether you can tell me. If you go through this, go through like this, you will know. 1, starting pointer at B, B pointing at 0, and 0 not pointing at anything. So, what is deleted? D is deleted, no? There is no link to D from anywhere to 2. So here, that's a conceptual diagram of a linked list and a free list. So I told you that free list has to be there in order to get, when you're adding new ones, you have to know. So it's like this, start pointer and BDL like that, and the null pointer there. Similarly, another one will be there with no data or nothing and no pointers. The pointers are there. So free list pointer will point at this. So this is the first one to be added if you need one. A linked list and a free list implemented using arrays. So now a little bit gradually getting complicated, advanced. So start pointer is -1. Free, both are empty now. Free list is also empty. A linked list and a free list implemented using arrays. So before any data is added, start pointer here is -1 and free list pointer is 0. So free list pointer, from the free list pointer only you will take. So it's here, no? 0, free list pointer. If you look at this, this is the one. So if you want to put data, it will be here. And -1, start pointer is pointing at this one. That means there's nothing. It's not pointing at anything because this is the end of the list. Assume L, B, and D were added to the linked list and to be kept in alphabetical order. This is very interesting. This figure 30.26, this one, shows how the values are stored in the data array and the pointers of the linked list and free list adjusted. Now, watch and follow carefully. The start pointer, now you are entering B, L, B, and D in the alphabetical order. You have to assume L, B, and D added in the linked list and be kept in alphabetical order. So, L, B, D will be L is here, B is here, and D here. Right? So, how? Start pointer is 1, which will be B. Not L, not 0. If it was 0, then L, the last one. In a descending order, it would have been 0. But now alphabetical order means ascending. So pointing at B, then B pointing at D, and D pointing at L. And what is the free list pointer? It's 3. That means the next one is this. The next one to come is this one here. And then the L is the null pointer there. Is that clear? Okay. Now let's see any more operations. If the node containing D is to be deleted, if the node containing D is to be deleted, the array element of that node needs to be linked back into the free list. There is another additional work there. Figure 13.27 shows how this is done by adding the node to the front of the free list. So what we have to do, link list and free list implemented using arrays. So D is to be deleted. D is to be deleted. What happens? Start point is 1 as usual, and the change needed is only here, where the list is concerned. The change is, instead of making it 2 going to D, stop going to D by making it 0 here, and that's it. D is deleted. But free list pointer, now this D should be able, this pointer or this node should be available for later use, for the next use. So what you do is, early it was 3, no? Yeah, it was 3. The next available node was 3, index number. Now we are making it 2. So in 2 places we are changing. One is the last, you bypass this, and the other one is make the free list pointer. That means this is available again. So the next time you add something, D will be overwritten. D is not erased, D is still there. But it will be overwritten because the next free list pointer is 2. As if it's not there, you know. It's invisible, like. Think that it's invisible. So that's interesting. Now there's a task. A linked list needs to be set up using the values in the user ID array shown below. So there are user IDs and the start pointer. There are some user IDs. Without moving any of the contents of the user ID array, insert the pointer values so that the linked list is in alphabetical order. So what you have to do? You have to find the first element. First element is this, no? First node is AS23 because I'm doing in alphabetical order. AS23, the pointer, the index is 3. So what do we have to do? Start pointer will make it 3 here. So that will start from here. Then the next one should be B. So B has the index 0. So from here, it should be 0 here. It will go there. And the next one, after B, it will be C. CK25. So 2 will be the pointer here. And then C will point at D, that is 4 here. D will point at F, 1. So against D, it will be 1 here, it will go there. And that is the last. No? That's the last one. So here you have the null pointer. Very easy. In section 30.02, we looked at the user-defined record type. We group together related data items into record data structures. To use a record variable, we first defined a record type. Then we declare variables of that record type. We can store the linked list in an array of records. See, we can make use of that. One record represents a node and consists of the data and a pointer. So there are 3 items to have in the record. Now we are going to declare this as a record type. So that will be, so that it's very easy. You remember the book type, the person type, where you have like a record and the fields inside. So here also we have the fields there. What are the, then we can declare, we can store the linked list in an array of records. One record represents a node. So one is a node, one node, and consists of the data and a pointer. So actually there'll be data and the pointer, like a record, 2 fields. Then you can process the way we want it. Only difference here is we are talking as the list array. We are putting this into an array as a record type. Like how we created an array of 100 records for the book type or the person type. Similarly, you can create here also. So a linked list before any nodes are used. In this case, It's like this, a record. Now, earlier we had two arrays, one D array here, one D array there. But here is one array with both together record. Tip, a stack can be implemented from a linked list. The start pointer is seen as the top of stack pointer, and a date item is only added to the start of the linked list, and a node is only removed from the start of the linked list. So you can adapt it to stack also. A queue can be implemented from a linked list. The start pointer is seen at the front of the queue. Data items are always added to the end of the linked list, and items are always removed from the start of the linked list. So deleting, inserting, adding, you learned all that. So that comes to the end of this chapter 13. So that was quite a long one and important one. So please go through again and again and be thorough with it. All right.